In this video, we're going to talk about Michaelis-Menten kinetics, which is a really important way to think about the rates of chemical reactions in a cellular context. So let's tackle that. So imagine for a second that you have a cell and you're interested in a particular reaction that's happening in that cell. And you want to know how fast is that reaction going given what I know about what's happening in the cell. This is a good point to pause and think about it for a second, but what sorts of information would you need if you wanted to actually do that? If you wanted to guess or to estimate how fast a reaction is going in a cell? So go ahead, pause that for a second. What do you need to know to guess how fast a reaction is going in a cell? Okay, turns out that you can get at this with actually if you know four pieces of information, which is how much of the substrate is around, how well does the enzyme recognize the substrate, how fast can the enzyme catalyze the reaction when it's bound to substrate, and then how much enzyme is around. And it turns out if you know these four pieces of information, you can plug this into a really helpful and powerful piece of mathematical machinery called the Michaelis-Menten equation. So it's shown here at the top. We'll unpack it in a little bit. I just want to mention really quickly, it's named after Maud Benton and Leonore Michaelis. Maud Benton is actually a really fascinating person. It's totally worth reading more about her. But she did a medical degree in Canada, and then they didn't allow her to do research because she was a woman. So then she went to Berlin and did research there. And then she went to Chicago. She did this, but she was a very early pioneer in physical biochemistry, and she did it the whole time being a pioneer as a woman scientist too. So really a cool story. So totally check that out. But with that aside over, let's talk about the Michaelis-Menten equation itself. So what are the parts? What is it used for? So I said that you needed four pieces of information. What are those four pieces of information? How are they coded into this? So how much substrate is around is given by this term S naught, substrate concentration. We'll talk about details on that in a second. How well does the enzyme recognize substrate? That's given by this thing, Km. How fast can the enzyme catalyze the reaction is given by kcat. How much enzyme around is given by this thing, E total, enzyme concentration. And then this is how fast. So I should have put that one on there. And so when you look at this, hopefully you can see, oh, yeah, I can see how I could plug numbers in and get an answer. Maybe you don't quite understand how the parts are put together yet, so we're going to take that apart. All right, so let's make a graph of this here, what this thing's going to look like. So what I'm going to do is I'm going to plot V naught on this. So this is the velocity of the reaction. And we'll worry about the naught in a second. So for the moment, this is just how fast the reaction is going. And then down here, this is S naught. This is the substrate concentration. So as we add more substrate, what does the velocity curve look like? This is actually another good point to pause and think about this. So what is the velocity curve going to look like? Is it going to go up? Is it going to go down? Is it going to swirl around? And when I'm teaching a class in person, I have students like wave their hands. It's really fun. So wave your hand in front of your screen. What is this curve going to look like if I do a graph of S naught versus V naught, or V naught versus S naught? Turns out the curve looks like this. Now we talked about this kind of curve in my video about binding. If you've seen it, I said something about when something does a saturation behavior, that tells us something is happening. What does it tell us? It tells us something is running out. Wow, that is terrible writing even for me. Something is running out. We're running out of something in this situation. What are we running out of here? We are running out of enzyme. That is the key thing that this models. It models the fact that there are a finite number of enzymes. There's not an infinite number of enzymes in a cell. If you add enough substrate, eventually you're going to run out of enzymes. We've also seen a curve that has this kind of shape before, a saturating curve. And that curve looks a lot like this, but it has this thing theta. And recall that theta would be mx over m plus mx. This is the concentration of a macromolecule that's bound to some small molecule x, has this kind of shape. Turns out that is given by this x over x plus kd. And what do you know? That is exactly what's here in the middle. This Michaelis-Menten equation has built into it a binding equation. So I said that our velocity, as your substrate concentration goes up, your velocity sort of saturates, it runs out because we're running out of enzyme. And we can see that that's being modeled in this by a binding equation. We're basically seeing that as enzyme binds, we run out of enzyme and we can no longer go any faster. Okay, so this thing here, S and Km is measuring, make myself go away, substrate affinity. It's behaving exactly like a KD. It's saying, what is the affinity of the substrate for the enzyme for the substrate? What is the affinity of the substrate for the enzyme? We talked previously about steroid receptors. We could say, what is the affinity of the estrogen receptor for estradiol? It's, I don't know, whatever the number was, 0.1 nanomolar. Here it's the exact same sort of thing. We can say, what is the affinity of the enzyme for the substrate? It's some number of micromolar or millimolar usually. Okay, that's measuring that. But this is giving us a velocity, right? A rate. This has no units, actually, right? This is concentration over concentration plus concentration. So this has no units. This is a fractional saturation. So kcat is giving us a rate. And what it's measuring is the catalytic rate once bound. So once the enzyme is engaged with the substrate, how quickly can it go? So this is the catalytic rate. So Km is measuring affinity. Kcat is measuring catalytic rate. Okay, so that's just kind of phenomenologically, that's what we're seeing. We're seeing, all right, we can measure velocity, we got this binding curve shape, it's got the kcat, whatever. What are we actually modeling here? So the equation we're modeling looks like this. Enzyme plus substrate is in equilibrium with an enzyme-substrate complex, which then goes on to enzyme plus product. This has a relationship kcat. So this is the equation that we're modeling. I want to talk about the assumptions and then what this actually looks like, what we're actually assuming here. So we're making two assumptions in this Michaelis-Menten analysis. Sometimes people talk about three, but really we're making two and the third follows. So the first assumption we're making is that enzyme substrate to product, I guess enzyme plus product, make this balanced. So the final reaction on there is irreversible. So we never see product going back to substrate, we just see substrate going to product. The second assumption we're making is that enzyme plus substrate, this first reaction going this, is fast and reversible. So the last reaction is an irreversible process, and this is a fast reversible process. Oh, and I should say fast here. By fast, I mean faster than kcat. So kcat is relatively slow. This is relatively fast. And this is actually a mathematically exact analogy for this. Turns out if you go to this YouTube channel, you can get a link to actually buy one of these machines. So maybe you should go do that. Maybe I can get this guy to sponsor me. But the basic idea of that we're seeing here is this is like I said, mathematically exact representation of Michaelis-Menten kinetics. So what we have are a bunch of balls that are bouncing around. They're being randomly bounced around. They're engaging here with this position, which I'm going to call the enzyme-substrate complex. Each of the balls are substrates. And so we have this rapid K on, K off, K on, K off, right? The balls are bouncing in and out of this very, very rapidly. But then every once in a while, we have a slow process that's kcat, what is the rate that the reaction happens, that the ball comes out of the thing, and then once it comes out, it is irreversible. So if you're thinking about an enzyme active site and you're thinking about a substrate binding, substrates binding and coming out, binding and coming out, binding and coming out, binding and coming out really, really fast, as it's doing that really fast process, occasionally you'll have kcat happen and it will turn into product. Okay. So that's what we're trying to model. Are those reasonable assumptions? Well, it turns out they are with how we're going to get to these values. So how do we get to Km and kcat? Remember, those are our measures of affinity and rate. How do we get those values, right? So we could actually use those to, say, study if something happening inside of a cell. But actually, we need to go back before we get there and ask, how do we get to V naught, actually? How do we get to this thing here that we might experimentally measure? And it turns out we get to V naught in an experiment. So here is the experiment we might run. What we're going to do is, as a function of time, we're going to measure the accumulation of product from a particular starting concentration. So I'm going to say S naught equals 1. I just made that number up. But what we will see is S naught equals 1. If you imagine you can follow product over time with, say, a color or something, you get a curve that looks something like this. Now, this is a point of confusion, and I've decided this is because biochemists hate everybody, but it's actually part of the physics of the universe. But basically, we have two things happening here that have the same kind of shape. This curve is not the same as the curve that we saw previously, which was substrate on the x-axis, concentration on the y, or velocity on the y-axis. This is time on the x-axis, product concentration on the y-axis. These have different shapes, or they have the same shape, but different underlying things that are happening, right? So what's happening here is we start with no product. Here we reach equilibrium. We've accumulated all the product we're going to get. Okay, so cool. What do we do with this? What we can do is look at the very first step of this, the first couple of points, if we're, say, measuring this. At that point, we know two things. We know that S naught equals 1, and we know that product formation is irreversible, right? Because we don't have any product around to begin with. The only thing that we're seeing is a reactant going to, or a substrate going to product. So it turns out this is V naught. This is the initial velocity of the reaction when we have some substrate concentration and no product around. We know the substrate concentration, and we know, so we can measure this velocity. Okay, so that was V naught with S naught equals 1. Now let's do S naught equals 2. So we added some more substrate, and so the reaction is going to go faster. Actually, we're going to get more product. We're going to get twice as much product, right? And that's going to give us another V naught. And so that's going to give us a second value of V naught. That's the blue value. And then let's do another one. So let's do S naught equals 3. So now it's going to be 3 times higher. And we're going to have a V naught associated with that, right? So you can imagine that what we can do experimentally is measure these V naughts, these initial velocities for reactions, as a function of substrate concentration, and that will let us construct a V naught versus S naught curve. And so I was actually doing it there in that form. So we're going to transfer this way. We're basically going to say, all right, our S naught equals here, and this is our V naught. That's the initial rate of this reaction, right? So for 0, which I'm going to do in orange, our V naught S naught is 0. For red, maybe it's there. This is 1. And then I had 2. Let's put that there. And then 3. Let's put that there. Now I made up these numbers, right, schematically, but you could imagine here that this is what you'd see, right? So you measure what's the initial velocity under s equals 1 under red. You measure the initial velocity under s equals 2, blue. You measure the initial velocity in s equals 3, the black one. You then plot those initial velocities versus the concentration, and you get out one of these Michaelis-Menten curves. Okay. So remember, though, our goal is to get to Km and kcat. And remember that those things have meaning. This is the affinity, and this is the rate, or the sort of rate constant for the reaction. How do we get those from one of these curves? Well, it turns out that Km, we already know how to do. So remember that this relationship, this equation looks like this. S naught over S naught plus Km times kcat times ET. This block here looks a heck of a lot like what we've seen before, right? With x over x plus kd. How do we get a kd from a curve? Well, we go to the 50% line, whatever exactly that is in this context. We drop it down, and Km is S naught at 50%. Okay? Now you might be saying, yeah, but 50% of what? And it's going to be 50% of V max. V max is saturated velocity. That's when all of your enzyme is bound up with substrate. There's nothing limiting it other than the amount of enzyme around and the rate of the reaction. That is the V max. It would be the equivalent of the theta equals 1. It's the point where the enzyme is fully saturated. So what is V max on this graph here? Well, V max is when the enzyme is completely saturated. What that means is this here should be 0, right? The concentration, you're at a very high concentration of S relative to Km. So the V max equals kcat times the enzyme concentration. So you can get to the Vmax by asking, where does it go? What is the highest curve on there? That's your Vmax. What's your Km? Km is the S naught at 50% of whatever the Vmax value is. And then what is your kcat? Your kcat is Vmax over your enzyme concentration, because if you're doing the experiment, presumably you know your enzyme concentration. Okay. So what does that mean? That means that we can describe any enzyme, any Michaelis-Menten enzyme, in terms of a Km, which is the affinity for substrate, which we get the same way we would get the affinity for any other molecule. We look at the concentration of half of its activity. And we can get kcat, which is the fastest the enzyme can go if the enzyme is fully loaded. If this fractional saturation is at 1, so it's fully loaded up, how fast does it go? What is the kcat times the amount of stuff we have? Okay. A couple of cleanup points that are cool and interesting. The first is that one of the things that biochemists often describe is kcat over km. And this is basically a ratio that says how often do the enzyme and the product, the enzyme and the substrate collide productively. So this is in rates, so this is in per seconds, and this is in concentrations in moles. So it's basically the seconds per molar per second. How quickly is this happening? And it turns out that you can actually discover when a reaction is diffusion limited or not based on this reaction. So basically, if you know the size of the molecules, you know how fast they can diffuse. There are some really nice physicsy equations that say how quickly, big things versus small things diffuse into each other. And if that rate is up there, is high enough, what that says is you actually have a diffusion limited reaction. Basically, if this kcat over km is really, really high, that says you're now, instead of being limited by the formation of this transition state and all these things, you're just limited by the stuff running into itself. Last bit of cleanup I want to put in here, and then we're actually going to be done with this, is we've talked about kcat and km as though they're kind of a feature of the enzyme. But really, they're a feature of the enzyme with a particular substrate. So for example, this is the enzyme fumarase, which is an important enzyme in the citric acid cycle. It interconverts between fumarate and malate. And hopefully what you can do, those are kind of small, I'm realizing, but you can look at these and say, oh, what is kcat? It's 8 times 10 to the 2 for fumarate. It's 9 times 10 to the 2 for malate. And then they have pretty different KDs. The km is 5 times 10 to the minus 6 for fumarate and 2.5 times 10 to the minus 5 for malate. So what this means is the enzyme is recognizing these things slightly differently because they have slightly different structures. Okay, that was a lot of stuff, but what do we say? Well, first of all, we said that enzyme kinetics are described using this thing called the Michaelis-Menten equation. In reactions in a cell, the number of enzymes is often limiting, which means we have curves that look like this. As we increase our substrate concentration, our velocity ends up leveling out. The Km is a measure of the affinity for the substrate. So that's something like right there. That's the Km. The kcat is the rate of the reaction that's catalyzed by the enzyme once the substrate is bound. And you can read out these curves, these kcat and km values, by looking at these V0 versus S0 curves. Okay, so that's what I have on Michaelis-Menten kinetics. Hope that was helpful. We're going to be doing enzyme inhibitors, and then we'll be done with our enzyme series. So talk to you later.